Lost it.
It turns out that specifically just the curl is first of all the one that because you have but in particular all zero is so A exactly and it turns out that the only operator
Yeah. So he's right over there. Usually sits on that side. He usually sits on this side.
it has its own line.
So did everyone have an interesting time at lunch today? Oh, welcome to Colorado. We wanted that for your first week, but we couldn't get it until week 2, so we had to do it now. Hail is pretty common here in the summer, associated with thunderstorms. I've seen bigger hailstones. I mean, I've seen hailstones like this, which I was not seeing today. Really? but I do think this was the most intense hail that I remember seeing, at least in my years here. So you had a real Colorado experience. There's an issue that I want to warn you about that we're working on. Our coffee place called, and yeah, their power went out and their machine broke and there's flooding and they can't get us coffee at 3:15. So our staff is pursuing other coffee options, but I can't make any promises. I'm a little worried about 65 TASI students getting hailed on and then not getting caffeinated. So we're working on it. But I just want to warn you that is a situation in flux. Okay. That being said, we're ready for Ken Part 2. You only had to wait a few hours from Ken Part 1. So take it away.
Thanks. Yeah, so I was starting to talk about this two-level system that Nadi talked about as kind of a warm-up to quantum supersymmetry. And so the idea is we have two states. Nadi talked about how there's this SO3 symmetry that acts on the operators and a SU2 symmetry that acts on the states. And so let's write the states as some kind of doublet under this SU2. And I'll write it as fermion and boson. And so this is the doublet. And I have in mind that we can define some operators which will be like fermion operators. And so we'll say that we have some operator psi and some operator psi dagger, which anti-commute. And I'll think of psi as an operator that, psi dagger, let's say, is an operator that acts on the boson to give a fermion. So it's like a raising operator. And then psi is like a lowering operator. And we could write them, if we want to, we could also write them in terms of real components. So I'll say that we'll have some psi f, so these are complex, and some psi g, which anti-commute to give delta fg, where here f and g run over 1 and 2. And so this preserves some SO2 subgroup of that SO3 that Nadi was talking about. And there's a natural action of U1. So we could see that if we write in terms of these complex ones, we could assign some U1 charge. And so let's say that we'll assign, since this is like a raising operator, let's say that so there's a U1F charge which we'll say is 1 for that one and -1 for that one. So now this U1F, we could think about it as a subgroup of the SO2. Well, we could think about it as embedded in the SU2 that acts on here. And then we might want to assign charges maybe a half and minus a half to make it symmetric. And that this is like fractional fermion number that you sometimes see. But we could also just add a constant to that, and we could assign them to be charges fermion number 0 and fermion number. So we'll say that we have two states. I'll just write it again, that there's this Bose state, and then there's this fermion state. And we'll assign this as having fermion charge 0. This one has fermion charge 1. And it was mentioned at the end last time, we want to look at something like trace -1 to the f, e to the minus beta h. So that's where I'm going with this, is we want to define -1 to the f is, +1 or -1 for these two states. Maybe I don't need to write it since it's kind of obvious. Maybe I'll just write here. -1 to the f is 1 and -1. Okay, so now if we look at this partition function, where if we look at trace -1 to the f e to the minus beta h, what we could see is that if these two states are degenerate, then we're going to get 0, because one of them will have charge +1 and one of them will have -1. So we'll just get 0. And I mentioned that we could think about this as a path integral, where, so we do some kind of path integral to the minus Euclidean action, where we have boundary conditions so this is Euclidean time is okay, so thanks to the -1 to the f, we have periodic boundary conditions. If we didn't have the -1 to the f, it would have been anti-periodic boundary conditions. And from this point of view, we can also see why we would get 0, because if we have periodic boundary conditions, then there's a 0 mode for this psi, which is just, let's just call it psi 0. And for d psi 0, then we basically use these rules of Grassmann integration. So I wanted to anyway mention Grassmann integration for talking about superspace. But basically, if we have a d psi 0, it behaves like a Grassmann integral, and we get 0. The rules of Grassmann integration are that if we had something which is anti-symmetric, we get 1 if we have psi 0, and otherwise we get 0. And this is called soaking up the fermion 0 mode. So here we'll say that there's a fermion 0 mode. And it's thanks to that fermion 0 mode that we end up getting 0. Whereas here we would say if we insert this psi 0, we've soaked it up. I don't know, this was how we described it. Maybe there's some other phrase for it, but after like walking through these puddles, so, we can soak up the fermion 0 mode to get something non-zero. Okay, so in this case, we get trace -1 to the f e to the minus beta h is 0. So I wanted to use this as a warm-up to talk about supersymmetry. And supersymmetry, we could consider supersymmetry in different space-time dimensions. And the idea of supersymmetry generally is that we have some conserved charge or charges in the spinor representation of the Lorentz group, which in some sense square to the Hamiltonian, or to the energy operator. So for instance, in 4D, what we would write is we have a supercharge, which has a chiral spinor index. So here this alpha, if we think about the Euclidean Lorentz group, well, we could either do it in Minkowski space or Euclidean space. But basically, we could think of the Lorentz group as, let's just write it as like spin. And if we think of this as roughly like SO4, which is like SU2 times SU2, then there's a left chiral index and a right chiral index, and this alpha runs over the spinor index of this SU2. So it's a two-component spinor index. So here alpha is 1 and 2 associated with this one. And this is a Wesson-Bagger type notation. We'll use alpha dot, which is running over 1 and 2. Sorry. 1 and 2, 1 and 2, and that's a spinor index of that one. So in 4 dimensions, we will have a conserved charge, Q alpha, and also a conserved charge, Q bar alpha dot. So we have a left chiral spinor and a right chiral spinor. And the supersymmetry algebra is that these things anti-commute times p mu. So this is the 4D supersymmetry algebra. And so we know p mu the way p mu I can write as the integral d3 x of t mu 0. And likewise, Q alpha is the integral d3x of some current. So this is some current that has a spinor index and a vector index. So it's a conserved current, and then we look at the zeroth component of that, integrate that over space to get the charge. So, as long as we have some local theory are associated with integrals, some charge density. And likewise for Q bar alpha dot. So we have some, so maybe I'll write here that, maybe I should make this look more curly. Okay, there's some conservation law. And so I'll talk more about this, but I thought as kind of a warm-up, it would be fun just to talk about how this first shows up in quantum mechanics, just to try to make it a little bit simpler. So in this case, I would say that if we're trying to count supercharges, I would say that there are 4 supercharges, just because alpha can run over 2 indices and alpha dot can run over 2 indices. So we'll say here that we have 4 supercharges. And we could ask what would happen if we reduce this down to quantum mechanics. Like maybe we can take our space and, talk to the quantum mechanics if we throw out everything, throw out all the momentum modes on the T3. So we can look in general in quantum mechanics. So quantum mechanics with n supercharges. Let's call them QF. So here F is just a label that runs from 1 to n. And you know, so this F would be like this alpha and alpha dot once I reduce down to quantum mechanics. I would say that I have four different choices. And the algebra, which is what you get if you reduce that algebra, is QF, QG is 2H delta FG. So basically, what this is saying is that each one of them squares to give the Hamiltonian, and they anti-commute with each other otherwise. And, okay, any questions so far? Okay, so one consequence of this that we could see immediately is that if we look at the commutator of the Hamiltonian with the QF, so we can just plug in the Hamiltonian here. It's the square of any of these Q's, and we can see that we get 0. So this algebra implies, as a consequence, that these charges are conserved. And another thing that we can do is we can write let's write the Hamiltonian in a kind of a symmetric way as, oh, actually before saying that, I forgot to say something here, which is that this thing preserves a ON symmetry. So if we, like this delta FG, you know, is, if we can do it, we can do an ON transformation on the identity and just use the fact that it's the rotation times its transpose is 1 for an ON rotation to see that that preserves this. So this has ON symmetry, and this symmetry is what's called an R symmetry. So let's put here a little R. And R symmetry is just a name for a symmetry that acts non-trivially on the supercharges. So an R symmetry means that it rotates the Q's. So anytime you see R, it just means that the Q's transform non-trivially. Okay, so we can write the Hamiltonian as 1 over n. I goes from 1 to n. We can write it as the sum, as any Q squared. So let's just write it as in a symmetric way like this. And now we put that inside of, we can take any state and look at the expectation value of the Hamiltonian. And now we could put in this identity and write it as the sum on I goes from 1 to n. Sorry, this is, let's just write it like QF. I'll call it F. So F goes from 1 to n, 1 over n. And now what I want to do is I want to write it as the absolute value squared of QF and omega. And here I'm using the fact that I'm going to take these Q's to be real. And so QF is QF dagger if they're real. And so I put in the QF squared, and then so we had a sum of terms with QF squared, and then I can just rewrite it this way, because if I take the dagger of this, I'll get something that makes this equality true. Is that okay? So this is, so what we see, yes?
So why are the Q's real? Just by...
Oh, I'm just going to choose them to be real to begin with. Yeah. So I'm going to Grecian operators. Yeah. Later on, we might want to combine them with complex objects, but for the moment, like here also, I had in mind that these are some real fermions, and then we could combine them into some complex fermions. Okay, so this identity is interesting because it tells us that the expectation value of the Hamiltonian is the sum of terms, and each term, as long as the theory is unitary, should be positive definite, or let's say non-negative. So each term is non-negative, and so we would say that, for instance, if this were an energy eigenstate, we would say that the energy of this state would be a sum of, positive or non-negative and we could have energy being zero, if and only if each one of those terms vanishes. So the energy is zero if and only if each one of these things vanishes, which means that QF all of the supercharges would have to annihilate the state with energy zero. And this is the condition that we would say holds if supersymmetry is not spontaneously broken, and if this state is a supersymmetric vacuum. So a state like this, we'll call it a supersymmetric vacuum without spontaneous supersymmetry breaking. So if we want to check whether or not our theory has a state where supersymmetry is broken or is not spontaneously broken, we just have to check whether there's a state with zero energy. Okay. Any question about that? Okay. Let's see. What do I want to say? Okay. I'll move over here. Also, maybe I should also, aside from this possible state with energy zero, because this is a sum of non-negative terms, we'll say that this energy is bigger than or equal to zero. So in general, we have energy bigger than or equal to zero, and if it's equal to zero, then it's a supersymmetric ground state. So what we can have if we look at the representations, we can have some state with E equals zero, which is annihilated. So this is just one state. And now if we look at a state with energy bigger than zero, then, okay, so if the energy is bigger than zero, the Q's don't all annihilate it. And so we can act on this with various Q's to get more states, which will be degenerate in energy. So we'll have Q on that state. Let's just keep it. So we can act with one Q. We can act with two Qs. Depending on how many of these supercharges we have, we can act with various numbers of these Qs. And because of the commutation relations, so they anti-commute up to the Hamiltonian, and if this is an eigenstate, the Hamiltonian just gives the energy. And so basically what happens is these Qs act like the way that you can generate a spinor representation from a Clifford algebra. So these Qs act to give a of this ON symmetry. So this is kind of like what what Nadi talked about with the fractionalization in his talk, where the operators had some SO3 symmetry that acted on them, but then the states can form something in. So here we have this spinor representation, and if we look at it in detail, what we'll find is that let's see, right? So I want to so I wanted to mention that. So we have this O and R symmetry. Contains, so this is some continuous rotation that we can do, but one of the continuous rotations that we can do is like is to give all of the QIs a minus sign. So let's call that minus 1 to the F, which gives so that's a special case of this R symmetry. And again, we can now try to look at this quantity of trace minus 1 to the F e to the minus beta H. And what we'll see is that, so in this case, we have to decide what e to the minus beta H does. But, well, we know in this case, the energy is 0, and so the Hamiltonian is just 0. And so here we'll see that this is equal to, plus or minus 1 on so we might have some number of E equals 0 states. Maybe just to draw a picture, let's suppose, imagine that we have some kind of potential like this. And so here we'll say that there's two states with E equals 0. And we can just assign some number, minus 1 to the F, to them. So maybe this one, suppose this one has minus 1 to the F equals 1. And this one, suppose it also has minus 1 to the F is 1. I'll also mention what would happen if it had minus 1. But let's suppose that they both have minus 1 to the F equals plus 1. These would be the states with unbroken supersymmetry. This would be like some kind of metastable state where supersymmetry is broken, because we see here, if E is non-zero, then some of these are going to be non-zero, and then supersymmetry would be broken. Maybe so this is like the spectrum of the Hamiltonian. Here I have in mind some potential. Okay, so that's on the E equals 0 state. Now, if we look at the states with E non-zero, yeah. Oh, sorry. Yeah, so I should have written the trace. So minus 1 to the F is plus or minus 1 on those E equals 0 states. I'm going to talk about the trace in a second, but for the moment, I just want to say what's minus 1 to the F. Yeah, thank you. I wanted to say what's minus 1 to the F e to minus beta H on each of these different states. Okay, so in this case, on the ground states, it could be plus or minus 1. And now what about on the states that aren't the ground states, like on this one with energy bigger than 0? So in that case, we'll have some Hamiltonian that's non-zero, but what we'll see is that the states with E bigger than 0 always so when we look at the states with energy bigger than 0, we'll see that some of them are like this boson state, and some are like the fermion state, and they have opposite charges. So basically, there'll always be like some boson state and some fermion state, which has -1 to the f is 1, and -1 to the f is -1, and they're related by some one of the supercharges q. This is just part of this spinor representation. So the spinor representation will always have some kind of pairing, where for every state there will be a state with opposite -1 to the f, and basically they'll just cancel in pairs. So if we were to look at the spectrum of the Hamiltonian, so let's say that like the states like this have -1 to the f is +1. The states like this have -1 to the f is -1. And so if energy is non-zero, they'll always pair up. And then at E equals 0, they might be unpaired. So this is E equals 0. So here we would have some ones that are unpaired, but everything for non-zero would always be paired. And so they'll cancel for this trace -1 to the f e to the minus beta h. So in other words, this quantity only gets contributions from these supersymmetric ground states. So like in this case, this would be 2. And all of the excited states would cancel out. So this quantity trace -1 to the f e to the minus beta h. So this is the Witten index. What we see is that it's independent of beta. So only the ground states can contribute, and the ground states have energy 0. So it's just some number like 2 in this case. Actually, sometimes you could get some beta dependence if there's a continuous spectrum. So if there's a continuous spectrum, then there might be some density, and then you might actually have some beta dependence in some case. But here I'm assuming that there's no continuous spectrum, and so it's beta independent. And what we see here is that if it's non-zero, then there are some supersymmetric ground states. So SUSY is not spontaneously broken. Let's see, maybe that's too low, but. Okay, so like in this picture, supersymmetry is not spontaneously broken.
If it's 0, you still have SUSY. I mean, you still could have SUSY.
Yeah. That's exactly what I was just about to mention. So we could, So one possibility. So the comment was, we could still have a supersymmetric vacuum even if it's 0, because maybe like in that picture where I said both of the two ground states had -1 to the f being +1, maybe actually one of them had +1 and one of them had -1. So we could imagine that there's some kind of, and maybe this has, -1 and -1, and then we would say that there are two supersymmetric vacua, even though trace, in this case, trace -1 equals 0 in this example, and unless they're supersymmetric vacua. So indeed, that can happen. But the interesting thing is that now we could say what happens is we somehow vary the different parameters. So maybe this is some potential, and we could try varying the different parameters. And as we do that, the energy levels might move around. But so if we were to, picture these kinds of energy levels, the energy levels might shift around. But if this trace minus 1 to the f is non-zero, like in this case, these two ones are locked in at 0 energy, because if they were to move away, they would have to pair up with something with opposite minus 1 to the f. And if there's no such state, then they really can't move around. So they're kind of locked in. On the other hand, if one of them had plus and one of them had minus, then they could be lifted up. So like in this case, even though they're both ground states, we might vary the theory a little bit, and maybe we get some other potential like that after we vary some parameters. And the trace minus 1 to the f kind of has to stay the same as we vary the parameters, because it always just gets contributions from the ground state. And so it's kind of just counting the number of ground states with this plus or minus sign. And so in this case, we would say this is an example where there's spontaneous SUSY breaking. And actually, if supersymmetry were to play a role in the real world, it's not that the LHC ruled out supersymmetry in the real world, because all the LHC showed is that the scale of where supersymmetry might be restored is above the LHC energy. And what could happen is that the supersymmetry might be a good symmetry of the underlying interactions and everything, but it could just be spontaneously broken like this by the vacuum. And then if the symmetry is spontaneously broken, you don't notice it much. It's like what Coleman called a secret symmetry. So it still has some implications, kind of like a secret, and we don't notice it so much. And this would be what we want if supersymmetry actually exists in the real world, is that it should be spontaneously broken. And so if we want supersymmetry to be spontaneously broken, we want to have trace minus 1 to the f is 0 as a necessary condition. Actually, often trace minus 1 to the f, and here I dropped the e to the minus beta h because it only gets contributions from the ground state. And so we can just set that part to 1. This thing isn't always well defined because there could be moduli spaces of vacua. So I'll talk about moduli spaces of vacua where the Witten index might be not necessarily well defined, because we have to define. Here I'm just kind of counting ground states, but if there's a whole continuum of ground states, we have to decide what to do. But this was actually the application that Witten had with this Witten index, was to see whether or not supersymmetry is spontaneously broken by computing the Witten index.
Sorry, what do you mean spontaneous breaking of supersymmetry? Does the degeneracy of non-zero energy states still preserve, or that's also break somehow?
Oh, okay. Yeah. So the question was about the degeneracy of the non-zero states. Yeah. All the states can get splitting from the spontaneous supersymmetry breaking. Yeah. So that could explain, like, for instance, why the photon is massless. But if supersymmetry is right, there should be something like a photino, and we don't see a good candidate for a photino. But yeah, so it could get some extra mass from the supersymmetry breaking. So maybe I should have left more room for writing down properties of trace minus 1 to the f, but so I'll just write it here. Trace minus 1 to the f tells us whether or not supersymmetry is broken, but more generally, a useful thing is that it's independent of continuous deformations. Just for that same reason, because any continuous deformation that we do, it might shift around these energy levels, but trace minus 1 to the f only gets contributions from unpaired states, and those unpaired states can't possibly move to higher energy. if they made a non-zero contribution to the within index, because they would have to pair up with something, but there's no partner for them to pair up with.
So when you say continuous deformations, do you put any restrictions on them, as in they have to preserve supersymmetry?
That's a good point. So I'm assuming that these. So the question was, should these deformations preserve supersymmetry? Yeah, let's say that are SUSY preserving. Yeah, thanks. Uh-huh.
Interpretation of the within index is some sort of topological invariant.
Yes. I was just about to mention that, in fact. So, so the question is have an interpretation as a topological invariant. And so in Witten's paper from maybe 1982, he talked about a lot of connections between supersymmetry and math. And so like the connections between supersymmetry and cohomology and also Morse theory. This is what he won the Fields Medal for, was this connections between supersymmetry and math. And the context there was we could look at some theory where the target space so we have like some nonlinear sigma model. Yeah, so for example, trace minus 1 to the f could be, in some of these supersymmetric theories, like the Euler character of this target space. So like for instance, if we took our target space to be if we took it to be CP1, then trace minus 1 to the f is 2. It's the Euler character of a two-sphere. And so that would tell us that this supersymmetric sigma model on CP1 doesn't have supersymmetry breaking. It has always at least two supersymmetric vacua. Let's see, any other question? Yes, good. Yeah, so the question was, can one of the vacua through a continuous deformation go to infinity? And yes, that in fact can happen. And that's one way that the Witten index actually can change, is if you have vacua that come in and out from infinity. So yeah, there are definitely examples. When I said that this is independent of continuous deformations, I really should have said up to that are either going to or from infinity in field space. So if we, so that definitely can happen, is that we can have vacua that kind of run off to infinity. Yeah, thank you. I'll mention an example like that, I hope, if I have time. Okay. Yeah, so I wanted to eventually talk about 4D SUSY gauge theories. So a lot of this I phrased in quantum mechanics, but it's true also, in other space-time dimensions. And in 4D supersymmetric gauge theories, we can ask, for instance, pure Yang-Mills. With I'll talk about what I mean by n equals 1, but n equals 1 basically means minimal number of supercharges, 4 supercharges. So we could ask about, for instance, 4D SUSY gauge theories like pure Yang-Mills with n equals 1 supersymmetry. And these theories have a mass gap. And we can ask if supersymmetry broken or not. Well, we can't prove that they have a mass gap. That's like this Clay Prize problem, a mass gap, and there's lots of cross checks and things that I'll talk about from supersymmetry that suggest that they have a mass gap. So they're believed to have a mass gap, and we can ask, is supersymmetry broken? And this was one of this was in Witten's original paper as an application of the Witten index, was to compute this Witten index for SUSY Yang-Mills. So what we can do is we can look at trace minus 1 to the f. Where, so the idea was to take space on a 3 torus for space. So because this is an index, it should be independent of any deformation. So we could take it first to be on a very huge torus, and then it should be completely independent of the sizes of this torus. And so we could start off with a space-time that's in a huge periodic box, and then make the box smaller and smaller. And because it's independent of that deformation, basically we can just reduce to some zero modes of the holonomy of the gauge field around the torus. And so that's what Witten did, was he did a quantum mechanics calculation for like holonomy zero modes around the torus and got an answer. Actually, the original answer that he got was that it's the rank of the group plus 1. And then later that, more using some subtleties, that in general it's the dual Coxeter number of the group. Modulo things that I'll discuss in a minute. So this Hg is the Casimir of the adjoint with the normalization that H for SUN is n. So this is also, that's right, it is 2 of the representation. It's like the quadratic index of the representation. So, for example, for SU2, maybe I'll write it over here. So SU 4D n equals 1, SUSY Yang-Mills with SU2 gauge group. Witten argued that trace minus 1 to the f is 2. So the fact that it's non-zero means that SUSY is not broken. Since it's non-zero. And this is something that I'll talk about some like supersymmetric gauge theories with matter, and then we can try giving masses to the matter and decoupling them, and then we can recover that it's 2 for SU2. So the fact that it's 2, so I haven't, for the moment, I'm just saying this as Witten's result, and then I'll try to give some arguments for it coming up soon. But for fun, let me mention that this is, more recently, it's been understood that it's not the same for SO3. So SU2 and SO3 are the same in terms of the Lie algebra. For SO3, for the n equals 1, so actually, I'll remind you a little bit. I think Sakura mentioned some things about this. We could talk about, for SO3, there are actually 2 versions, SO3 plus and SO3 minus. So here I'm talking about SO3 plus. And for SO3, the SUSY Yang-Mills, actually, let me not say it this way. Yeah, let's just say SO3. Trace minus 1 is 2 cubed plus 1. And this is the one that kind of comes from SO3 plus. The Yang-Mills theory, has a theta angle, and I'll discuss how we can rotate between the two of them by shifting the theta angle. And so we end up with contributions from both of them. And so this is 9. And this 2 cubed is from a Z2 gauge theory. On this T3. So if you put this Z2 gauge theory on a T3, you get some 2 cubed different states. So this is like still just some appetizing, something that I wanted to discuss more coming up. But yeah, so I'll try to explain a little bit more about that. Any questions? Okay. Yeah. So I haven't yet said too much about supersymmetry aside from the algebra and this R symmetry and the Witten index. But so we can ask, how do we write down supersymmetric theories? I mean, the reason why supersymmetry is interesting is because we can write down theories that are non-trivial enough to be interesting, like this SUSY Yang-Mills. But that still have the symmetry. And one of the ways that we write down these interacting theories, so we want to write down interacting useful way to do that is by introducing superspace. We don't have to do it that way, but it's kind of nice. And the basic idea is that the way that we write down, if we want a theory that has, for instance, translation invariance, a nice way to do it is just to write down some Lagrangian and integrate overall space-time, and then we have translation invariance just because we're integrating overall space-time. And translation symmetry is in the same algebra as supersymmetry. And so we'll try to do the same thing where we'll get invariance under supersymmetry by integrating over some kind of superspace, and then that will give us kind of translation invariance in superspace. So that's the basic idea. So for example, oops. Yeah, it's not good when the chalk gets wet. So for example, in SUSY quantum mechanics, where we have these supercharges QF, what we can do is we can, so we have time, and now we can introduce some new coordinates that are kind of conjugate to these supercharges. And I'm not really going to pay too much attention with upper or lower indices. Yeah, so let's just say that we have some indices theta I. And so we can write some so instead of just saying we have operators, so these are some operators, they could depend on time, and they can depend on these theta i's, and these theta i's will take to be Grassmann coordinates. And so each theta I, if these are real Grassmann coordinates, each theta I, let's just write that they anti-commute with each other. Okay, so they all anti-commute with each other. They square to 0. And so we could just write this thing out as a Taylor expansion. And let's see. Yeah, so we'll write this as phi is equal to okay, so there's one component where so I'm going to just write this out as like a Taylor expansion in the phi's. So there's one component that I'll write as phi of t without any of these thetas. Sometimes people write a bar on there, which means we just set these thetas to 0. And then there's another term, which is theta I times some psi I. And then we can write more terms. And the idea is that this is going to give us our pairing between our bosonic fields and our supersymmetric and our fermionic fields. Okay, so if we do this, the supercharges, so just like we could write the Hamiltonian as I h bar d by dt, when we write it, how it acts on is differential operator. So we'll replace the Hamiltonian with this I h bar d by dt, and we'll replace the supercharges with qi is d by d theta I plus I theta I d by dt. So this is how they act as differential operators on this superspace, and then we can check that it satisfies that supersymmetry algebra that I wrote before. And it's also useful to introduce some other objects that are called di. D by d theta I minus I theta I d by dt. So here I'm kind of sketching in quantum mechanics language things that are worked out in a lot of detail in Wessenberger. So if you really want to see this like in 4 dimensions, you can look in Wessenberger, for instance. But the thing about these di's and qi's is they anti-commute with each other. So di or 0, and that helps to write down things that have supersymmetry. So we can get a supersymmetric action. One way to do it would be to integrate over t and to integrate over all of these thetas of some function of phi. So if we have some function of phi, then basically it's like integrating over t gives us time translation symmetry, and integrating over these thetas gives us invariant under these q's. And so we'll have something that's supersymmetric. And also, this function could be a function of these di's, of these d phi i's. Okay, so this is inside of the function. So these d's are just other ways to build up things that end up being supersymmetric. Basically, because they anti-commute with the supercharges, they're kind of don't mess up the fact that it's supersymmetric. Okay, any question? Yes?
Is there an algebra relation for D with this what the answer is like?
Oh, yeah. So I guess they the anti-commutator will be maybe it'll have a minus h. Maybe it'll have a minus 2h instead. But yeah, the d's are so basically the q's are interesting because they're differential. They're ways of expressing these operators of our, or these charge operators of our theory as some kind of differential operators on the space. And the d's are really only kind of nice because of the fact they anti-commute, we can use them to construct supersymmetric interactions. But they don't really have a independent meaning of superspace.
I guess I'm just trying to check why the action they're only like D square order.
Oh, yeah, no, I just ran out of room. Yeah, we can have more. We can have more d's. Yeah, we can have more d's for sure. Yeah, thanks. Yeah, I should have put it the dot dot. I should have given myself more room and put the dot dot dot. Yeah, so we can have more of these derivatives. Let's see. Yeah, and we can also impose some conditions. So in general, if we write down, in general, if we have enough of these thetas and if we write down this thing, we'll get something that's not an irreducible representation. And so in general, we can put some conditions on these to make it an irreducible representation. Yes?
So to raise and lower indices here, is that with respect to some invariant tensor R symmetry?
Yeah, in this case, because the R symmetry group is SON, I'm kind of assuming that I can just raise or lower indices without doing anything fancy. We can just raise and lower them with the Kronecker delta. I should have said when I was talking about the R symmetry that the R symmetry, like here we say this thing, the algebra preserves a SON R symmetry, but our interactions may or may not preserve that symmetry. And so, like here, we could definitely write down things that would violate that SON R symmetry. And then we might want to be more careful with how we raise or lower the indices. But yeah, here I really wasn't that careful just because I was imagining that we had the SON symmetry. Yeah, thanks. Okay, any other? Okay. Right, so let's... Yeah, so let's say a few more things about yeah, so if we go back to the 4D case, Okay, so this is for supercharges. This algebra it has a U1 R global symmetry. So the U1 R global symmetry rotates Q and Q bar by opposite phases. So here we could give a phase to Q and the opposite phase to Q bar, and that will be preserved. And so we'll say that that the R charge for Q alpha, we'll think of Q as being like a lowering thing, and so we'll assign it R charge -1, and the R charge for Q bar alpha dot we'll take to be +1. Yeah. So so let's. I want to now introduce chiral superfields. So I mentioned in general, if we wrote down a general function. Yeah, okay, so let's go back here. So in superspace, we could consider something like some operator as a function of x mu. And now we'll introduce some conjugate thetas to these Q alphas. And so there's a theta alpha, theta bar, alpha dot. Unlike the case up here where I was taking them to be real, here these are complex. And so there's like a theta, yeah, so there's theta bar, alpha dot. And we could write down general functions. And a general function like this would be reducible. And so we can impose some condition, and one condition that we could impose is that it's a chiral superfield. And basically a lot of the mileage of supersymmetry, not all of it, but a lot of the mileage of supersymmetry comes from restricting to these chiral superfields. There will be, so just to kind of jump ahead, what we'll see is that these chiral superfields behave in a way like a topological subsector of the theory. And so like they'll have operator product expansions that are where the OPE coefficients are just like constants. They form what's called a chiral ring. And so there's a lot of nice things that will come from these chiral superfields. So what are the chiral superfields? So we can say that they're in terms, suppose that there's some operator x. Maybe in my notes I called it x, but let's just call it big phi. So a chiral superfield would be something whose commutator with Q bar alpha dot is 0. We can also have anti-chiral. And they're usually written with a bar. A 0. And so this is how I would write it if I weren't using superspace. In superspace, what we do is we write phi as a function of x, theta alpha, theta bar alpha dot. And we impose a condition And the condition ends up being d bar alpha dot on phi is 0. Okay, so why it's d bar alpha dot instead of this q bar alpha dot is basically, it just works out that way. That we have this, this is the statement as an operator statement, and then this is the way that we would represent it in terms of it. The analogous thing is a differential operator on superspace. Yeah, maybe I can just refer people to Wessenberger for details. Okay, so we could expand out this phi, which is a chiral superfield, as phi of y plus theta alpha Okay, so these alpha and beta indices I mentioned are like SU2 spinor indices. And so I can make something that's SU2 invariant by contracting them with an epsilon tensor. And actually, why don't I just, so usually that's just written as theta squared. So maybe we'll just write here that this is theta alpha, theta beta, epsilon alpha beta, f of y. And here basically y times some numbers basically it's something that's annihilated by the analog of this d bar alpha dot. Okay, so what happens is that this is basically x plus some extra theta terms, and then those extra theta terms, if we re-expand it out, will give us various derivative terms. Okay. Oh, okay. Yeah, it's a strange difference from the perspective of the lecturer versus the people in the audience. I mean, the time just flies by. Okay. Okay, so we can make a supersymmetric Lagrangian. One way to make a supersymmetric Lagrangian is by integrating over, this is the Lagrangian density. We'll integrate over all of the thetas, this denotes the thetas and the theta bars, something that's called the Kähler potential as a function of these various chiral superfields and the antichiral superfields. That's one way that we could get something that's supersymmetric, is to combine chiral superfields and antichiral superfields. Another thing that we can do is we can integrate only over the thetas of some function only of the chiral superfield. And then to make it real, to make the Lagrangian real, we should add the complex conjugate, which is d2 theta bar of some w bar. So this is some function with some coefficients that could be complex, and this has complex conjugate versions of those, and it's a function only of the antichiral superfields. Okay, so the canonical scalar potential would just be the sum on I, phi bar, and that would give canonical kinetic terms. So this leads to the kinetic terms for the different fields. So the scalars would have their usual d mu phi term. The fermions would have their usual psi bar ID slash psi terms. So this gives kinetic terms. And more generally, general function, we would have a nonlinear sigma model. With a Kähler metric. G I j bar, which is d squared k d phi I phi bar j bar, which is often just written as k I j bar. So the subscripts just mean those derivatives. So in this case, the metric, if it's the canonical one, then the metric is just a flat metric. But if we had a more general function there, we could get a nonlinear sigma model. And okay, so the Kähler potential, and then the superpotential. So W phi I is called the superpotential. Maybe since the time is up, I should basically stop. But it leads to interactions which are like Wij. So this is two derivatives of W times fermions. And a potential V, which is Ij bar, I W bar J bar, where this is this metric. And okay, so these are like some fermion interactions, and then this is like a potential. This potential, by the way, is bigger than or equal to 0, fitting with what we said about the supersymmetry algebra, that it requires the energy to be bigger than or equal to 0. And the supersymmetric vacua are the places where we're at the zeros of this potential. And so the supersymmetric vacua are the places where these Wi's are 0. So I guess I've run out of time, but yeah.
I was just going to say, maybe it's worth pointing out that on the last line, when you write the superpotential, you're now thinking of it and its derivatives as functions just of the bosonic.
Yes, thank you. Yeah, I should have said that. Yeah, so basically here, let's put a line, and a line, and a line. And here also, I should put a line. And what these lines mean is that we set the thetas to 0. Yeah, so here, yeah, thank you. So here when I'm looking at this looks kind of messy now, but let's make it a small line. Yeah, so we set the thetas to 0. So this is what you get after you've done these integrations. So after you've done the integrations, the thetas are all gone. And so in these expressions, we should just set it to 0. Okay, any questions?
Sorry, so the Kähler potential is like combines with the d phi squared because of is it because of the theta bar that you pull out of the phi one, or?
Yeah, so the Kähler, basically the Kähler potential comes from these terms that I hid in these y's. So it's like if I write this y as having like a theta and a theta bar, then there's going to be a term which is like derivative of phi times that theta bar, and so that's what's going to give the the usual kinetic terms is from integrating out the theta bars in here. And then, yeah, for the superpotential, basically we can just see it. Like for the superpotential, we don't even actually really need these terms. We can just see it from expanding.
Well, let's thank Ken. I know you're all in suspense about the coffee situation.
Yes.
So the good news is we were able to find it's not going to be probably as high quality coffee as what we get from the store, but we did find a coffee machine. There's coffee and also hot water for tea available. So you can warm up with some toasty beverages. I'll see you for the next talk at 3:45.
So you mentioned this vacuum coming from Intriligator.
Yes.